This is a case study of volume wear analysis using the BEX software tool offered by Taicaan Technologies. There are many applications in industry and other places where the wear of an object is critical to the operation, and the Xaris instruments are very useful in being able to measure basic characteristics of wear. And once we have the data set, we can then load the data into BEX, and then we can use BEX to do a quantifiable analysis of the amount of material that's been lost or gained from a surface. In this example, to show you a photograph of the object, this is an electrical contact. The dimensions here are roughly just over 2 millimeters across this silver central region, and this object has been mounted on a copper base, which you can see behind. You can see from this that there's a region where some activity has taken place. In fact, this is the wear that's taken place from arc erosion. This particular switching device is silver nickel. It had undergone 3,000 switching operations with a DC current of 10 amps with a 14 volt power supply. And what you see is the consequences of that activity. What we'd like to know is the amount of wear that's taken place. So we need to know the volume of material that's either been added or lost from this surface. And from the photographic image, it's quite difficult to ascertain actually whether this is a loss of material or a gain of material. If we look at the data in the Taicaan color scale, we can see quite clearly that this object has a crater region, and that's shown clearly here. If we take a look at the cross section, again we can see the copper base where the arrow is pointing to on the left, and on the right, if we click on the pointer, we can get an indication of the height of the object just by doing this. I think that's also pretty obvious from the height scale on the right hand side, but if we've clicked 2 points here, and we can see that the delta Z in the lower screen here where the arrow is pointing to is 0.61 millimeters. Let's go back to look at the image. If we add some contours to this, let's just add a few more. We can see that the contours here are showing us that the top of the surface has a domed characteristic, so some sphericity associated with it, and in the central region you can see the region where the arc erosion has taken place and damaged the surface. I think it's fairly clear if we take a top-down view of this. Let's just zoom in. That actually what we need to do is we need to be able to determine the wear relative to a datum surface. So we need an underlying surface. And in this particular case, the best way of doing this would be to measure the wear relative to a spherical region. And I'm just pointing the crosshairs to a spherical central region here. So what we did is we basically remeasured this. So we took the original data set in the metrology frame and we just remeasured the central region. And that's my next data set. So I'm just going to, I've already preloaded that, and here it is. I'm going to change the color scale here to jet, and we don't have any contours added to this, but if we take a look at the three-dimensional representation, we can see now a very nice representation of the crater that's been formed, where I'm just pointing the crosshairs. We can see also the roughness of the underlying, or the basic undamaged surface here surrounding that. Let's add some contours to this, so we get a representation, and go back to the top-down view. Now you can see the line is drawn here. If we go to the cross-section, if we want an indication of the roughness of the undamaged surface, we can do that quite easily now. We know, and we can see this intuitively from the cross-section, that we have a circular form corresponding, of course, to the three-dimensional spherical form. So if we go to 2D parameters, and if we click a circle fit, it's already highlighted here. If we show that in the form, we can see the pink line is the circle fit that corresponds to the red raw data. And if we want the roughness now, simply the difference between the form and the raw data is the roughness in green, and now we see the roughness with an indication of the roughness scale on the right hand side here. What I forgot to mention is this data set is still 501 by 501, and it's just measured over a smaller area, so 1.5 millimeters by 1.5 millimeters, which means the grid spacing is smaller than before. So here on the info panel we can see the grid spacing to be 3 microns. So coming back to our parameters, let's move the line, just move it up. We have an RA of 0.912 microns, move it down a bit, 0.933, so we can see pretty consistent roughness of the undamaged surface here, 0.951 now. Of course, if we bring this over the region where the crater is, then we get quite a strange representation, because we're fitting a circle to a data set that's now, the red line is no longer circular, it has this damage, it has this crater effect. So let's remove that and remove the roughness and just have a look at what we have. So we can see here the crater at the small one. Of course, in this plane we can just put some pointers on here to get an indication of the depth of the crater, and we see here it's about 40 microns deep, this particular crater. Well, how do we determine the volume of the material here? Well, a very simple action is to remove the underlying sphere from the data. So how do we do that? Well, if we fit a sphere to the data set as shown, we're going to get a value, but the value is going to be affected by the presence of the crater and the data associated with that. So clearly the best thing to do is to remove the crater from the calculation. So if we go to the two icons on the top left here that I'm pointing to, the one that I'm currently pointing to is data selection. By clicking this, you can see a paintbrush has appeared, and if we come down to the screen, we now see that we have a circle drawn on the screen, and if I just click on that, this is just a conventional left click, you can see I'm just removing data. So that's one way of doing it. So let's put that back in. I'm right clicking and just pasting it back in. So this is just a cut and paste type exercise. What I can also do is just use the shift from the keyboard and just press the wheel on the mouse, and I can then just adjust the size of that particular circle, and we can find the size actually from the menu as well. But actually I just want to make sure that the region I'm selecting here is just bigger than the crater. It's not a precise, but so long as we're cutting into we're removing all of the surface rather that's being damaged, that's the main objective here. So let's click on that. So I've then taken away the damaged surface, and what I'm left with is a surface which is nominally spherical. So if I now fit a sphere to that, we can remove that sphere from the data and then have a datum which is flat. So let's go to edit, oops, turn the brush off. Let's edit our data. Let's fit a form and fit a sphere. So very quick calculation. Bottom left here you can see the sphere. It's 5.484 millimeters, and indeed you've also got the center of that sphere should you need that. But if we look at the surface here, we've now got a surface which is nominally flat, as shown by the kind of red orange colors. And if we just replace back in the data, coming back to the data selection, there's a little arrow here which I'm just highlighting, and here you've got the round brush, square brush, the size of the circle, which is currently 1.08 millimeters, and I'm now going to include all. So just by hitting that function, I'm replacing the data, and now I think you can see we have a very nice representation here of the surface. And I think you can see intuitively that from all of the views here that we have a nominally flat surface, and we have a crater region which actually has a crater rim which is higher, which is above the level of the datum surface. The key point of this is to determine volume wear. So let's go to the top-down view. Let's have a look at the cross-section, and you can see here where the cross-section is drawn, this is nominally flat, and you can see it's around 0, but a lot of this is below 0, where I'm currently pointing to, and then the crater. and to the right these values are slightly above the 0. Well, what we're interested in is the volume, and this is the first time we're focusing on the volume calculation, and we can see in the window that I'm now pointing to on the left we have surface area above the datum, surface area below the datum, projected area both above and below, and for this exercise the volume above and the volume below. Now this calculation is being undertaken for the whole of the data shown in the image. So just bring this line up. As we've seen before, I've just drawn the line here. If you look at this data carefully, you can see that much of these spikes are above 0 and some of them are below 0. What that means, of course, is that the volumes that are being calculated here, both above and below, are going to add to the volume that's associated with the feature that we're primarily interested in. So we have to be careful on selecting the region over which we do the volume calculation if we're interested in improving the accuracy of the calculation. Well, how do we do that? Well, it's very similar to the way we remove data. We come back to the brush, and we have the brush that we used to remove the crater in the first place. And what I'm going to do is I'm going to reduce the size of that. So I'm going to shift, and I'm just going to just rotate the mouse wheel, and I'm just going to bring this in so that it's centered on the feature that we're interested in. And you can see I have a position here where I've drawn a circle which is just outside of the crater, where I've got the higher red colours shown here. I'm just pointing to that, and then there's an orange ring beyond that. So I'm just going to draw this just around the orange ring on the outer ring, and I'm going to remove it. Well, actually that's not what we want to do. We want the inverse of this image. So if we go back, let's turn the brush off, let's go back to the drop down menu and simply click invert the selection, and now we have a region selected which only includes the crater that we're interested in. And in fact, if you bring the cross section down, you can see that in the cross section data as well. So we're only including the central region of this. Let's hide that. And now importantly, we have a volume calculation on the left, which has been calculated only for the region that's shown. So as you'd expect, the volume above is now smaller, significantly smaller than the volume below. So if you look at the values here, 30209, and then volume below, 203,624. So more of the volume has been removed beneath the datum surface than above. Now, just to finish this exercise off, let's replace all of the data. So we're going to include all again, and here it is. I'm just going to change the circle. Just remember the values that we had. I'm just going to change the circle here. I'm going to let's have the circle highlighted. Let's reduce the size of the circle, and another way of doing it is using the slider here, but that needs to be, oh, excuse me, I've got that as an active, so that's my mistake. Let's replace that, bring it over the region that we're interested in, and I've essentially made the circle smaller now. So the circle now is just on the orange ring, and if we click that, turn the brush off, invert the selection, and again we now have some values. So just to finish this off, there's no absolute definition on how you define the region. What I've shown here, it's important that the region is carefully selected, and also you're very careful on how you remove the underlying surface. And you can see we were able to do that very, very easily and very effectively using BEX, and now we're able to get the volume calculations for the amount of material below the datum and above the datum, as shown in the window on the left.